Okay, so let's make a start. Happy World Logic Day to everyone here in the room and also online. So it's great that so many people have joined us here and online. So World Logic Day is an initiative that exists since 2019. It was proclaimed by the UNESCO and the Association of the International Council for Philosophy and Human Science, CPISH, in 2019. And so it's celebrated each year on the 14th of January. And that was why that day, that was the death day of Gödel, and it is the birth date of Alfred Tarski as well. And I know at least of two other logicians who have the same birthday. One of them is in this room, to which we'll get later. So it's a lot of, when you here click on this icon, I could do that quickly, then one gets to a long list of international events hosted on this day. And so I could see events in Australia, China, Russia, Italy, Switzerland, Estonia, Spain, Portugal, Iran, Venezuela, Turkey, Nigeria, Germany, Mexico, Canada, Sweden, and the US. And probably have not mentioned all events, but really it's a worldwide initiative to celebrate the logic and the historic and recent developments here. So we have planned for 3 speakers today: Arnold Beckmann, Ulrich Berger, and John Tucker. Unfortunately, Uli is not available today. He is not well and specifically lost his voice. So sorry for that. We will keep to the schedule. We will have a talk now at 1 o'clock by Arnold, 1 o'clock our time, and at 3 o'clock then by John Tucker. So 2 former head of departments. So it's really a pleasure to have both of them here speaking on this World Logic Day. And the topic will be around computation. Also, we had some relationship to computability. And the first talk is given by Arnold, and he will talk about computability. And so maybe we can switch now, sorry, Jay, to the first talk, to the slides. So the first talk is given by Arnold Beckmann on Provably total NP search problems. And Arnold is, as I said already, was the head of department for many years. And he did his PhD in Münster with Wolfram Pohlers, for whom he gave 2 memorial talks last year. Actually, he did a postdoc in Oxford and in San Diego, and in Vienna, and then joined us here in Swansea in about 2004. Yes, 2004. And so we are happy to have him here as speaker. So the stage is yours.
Thank you very much, Monica. Okay, thanks everyone. First, of course, the organizers for giving me the stage, and thanks very much for the kind words, Monica, and everyone who is joining today. So I want to give my a specific view, which I quite like, on computational complexity via a logical sense, namely through total NP search problems. And I'm also kind of giving a bit of my heritage with it. So Monica mentioned that I come from Münster, so I'm a proof theorist. I've done ordinal analysis, and all these kind of play a role, an important role in my research, in particular also in this topic. So what I'm aiming for is that I will start to speak a little bit about the heritage. I really set it up a bit broader, and then speak about one of the main logical frameworks for characterizing computation complexity, bound arithmetic, then come to the main aim of this talk, total NP search problems, and then give 2 applications of characterizing those, and then I will conclude. So the heritage. So I have 4 eminent logicians from the previous century who really influences this type of work, and in particular myself. One is, of course, Giuseppe Peano, and I'm mentioning here for the Peano axioms. And I will have another slide that I assume most of you will know what it is, but there will be a brief reminder. Then, of course, Kurt Gödel. Monica, you mentioned that it was his birthday?
Death date.
Death date. Today. Okay. And so I mentioned Kurt Gödel, one for his completeness theorem, which allows us to reason about these logical structures, like in complexity, with mathematical means. Yeah, that's what completeness is about. But then also his incompleteness theorems. And we will see later why the incompleteness theorem, what kind of role it can play here, why I'm mentioning it. I want to mention Georg Gensen. For one, he gave us the secant calculus, which is an important tool which proof theorists need to know about, but which in this context really is being used very widely. But also for something else, which I will mention on the next slide. And finally, of course, I cannot not mention Alan Turing, because without him we wouldn't have computational complexity theory as we currently have it. Yeah. So this is kind of where I want to start. Now let me go into aspects of this in a little bit more detail. So let's start with Peano arithmetic. I just make a brief introduction to those, because I assume most of you will know what I'm talking about. The domain are the natural numbers, so it's a theory of first order logic. We have a very limited language. It's not expressivity, which is the key purpose of Peano arithmetic. It's about simplicity, but also richness in terms of what you can capture there. So you have a limited set of non-logical symbols, 0, 1, plus, times, and the less than or equal relation. Defining equations, finitely many, so that you get sufficient properties of those to define them uniquely over the intended domain. But most importantly is the scheme of full induction. So you all know your induction formula, and if I say full induction, it means that you have this as an axiom for any formula in first order logic. Any first order formula in your language, you can have induction. So that will be a crucial setup for the logical theories, which we will be considering. Okay, so that's Peano. Then I have Gödel, and I'm mentioning here the second incompleteness theorem. You probably recall that there was this crisis in mathematics at the beginning of the previous century, so around the beginning there, in that inconsistencies were cropping up. And David Hilbert proposed a program to show once and for all that there are no inconsistency in the axiomatic setup of mathematics. And Gödel famously showed that, okay, that's not possible, at least not within a theory. You can't show its own consistency. And in particular, if you apply this to Peano arithmetic, there is a formal statement expressing that the axioms of Peano arithmetic do not produce any errors. And the second incompleteness theorem says that Peano arithmetic cannot prove this type of consistency, and that is true for. So there's this general theorem behind that. So that is one statement which I wanted to mention here. So you have a means of showing that something is not provable in a theory. And the final one is, so Gensen, in addition to the secant calculus, also provide a consistency proof for Peano arithmetic. So he identified what else you need in order to be able to prove consistency. So and here comes a little bit of my heritage. So I come from Münster. Münster at the time was famous for doing ordinal analysis. So using ordinals like epsilon naught in order to characterize the strength, in particular the consistency strength of theories. And in this context, so this is transfinite induction, so you have to extend induction, this principle, to longer well-ordering is not just the one for the natural numbers, namely the one for epsilon naught. And if you add that scheme to Peano arithmetic, then this is exactly what you need in order to prove the consistency. And I'm mentioning this because this ordinal will appear in the context of Peano arithmetic a couple of times here. Yeah. Okay. So this is all very high level. For those who have seen these things, you feel really comfortable. The others, for whom it may be new, may feel exciting that these things exist. Okay, so this is kind of the context of Peano arithmetic. Then the other context is that fragments of Peano arithmetic had been studied. So this started with Kirby and Paris, I think at the beginnings of the 1970s. And if we speak about fragments, then this is that you start to not have the full scheme of induction anymore, but you look at delineation of induction. So you start by delineating the quantifiers by counting alternation of unbounded quantifiers in front of something which is simpler, usually bounded or could be primitive recursive. So for here, bounded is enough. Yeah. And if you have these n alternation of unbounded quantifiers starting with an existential one, that's called sigma n. And if you restrict induction to just formulas of this type, then this is called, the theory is called I sigma n. Yeah, and they started to kind of introduce that and study their properties. I just want to mention one theorem which was proven at the time as well. It was by Charles Parson, who showed that if you take the first of those theories, I sigma 1, then the provable recursive functions in this theory are exactly the primitive recursive functions. Now, I assume everyone knows what primitive recursive is. Provable recursive are simply those recursive functions whose totality can be proven within the theory. So you could think about, okay, you just have a description or you have a formalization of Turing machine computability. You take an index of a program, and what you need to prove in the theory is that this program on any input terminates. That then you say that the function which is computed by this program is provable recursive in the theory. Okay. And again, this is a kind of a prime example of how you use theories in order to characterize here levels of computability, I should say. Yeah? So primitive recursive being the simplest one. And later, the provable recursive functions of Peano arithmetic had also been characterized, and I'm citing here one of those, or a couple of authors who did this. And again, this ordinal epsilon naught crops up here, and that is not a coincidence. There are deep reasons why the proof theoretic ordinal of the theory is also characterizing the provable recursive functions. So what this means is kind of you need to extend recursion along ordinals. So you also need to extend the recursion to the infinite in some way. And if you do this for any fixed ordinal below epsilon naught and allow this as a scheme, then this is what we call the less than epsilon 0 recursive function. And that is exactly the class of functions which is provable recursive in Peano arithmetic. Okay, and that concludes my heritage. Yeah, so this is kind of, these were things which I learned as a student, back and forth, and stronger theories, etc. Maybe not so much the fragments, because the school in Münster was really more interested in theories which are as strong as possible, because that was kind of also the quest of whether those theories, when they become stronger, are really consistent or not, or what can we do in order to justify their consistency. So what I want to do now is I take this as the background and now come to bound arithmetic, which is intended to be a logical framework to speak about complexity classes. So complexity in the sense not of primitive recursive and stronger, but in terms of polynomial time computable or non-deterministic polynomial time computable functions, etc. Yeah. So there were various approaches to a logical framework with that intent. Yeah. So the first one goes actually back to Steve Cook, who came up with equational theories who exactly achieved that. Yeah. So they were able to formalize and reason about polynomial time computable function in an equational setting. Sam Bass choose a formalism which is aligned to Boolean arithmetic, and then later Zambella introduced it, and Cook and Nguyen built on that one and had a really fat yellow book about that. They extended this setting to a language with two sorts: one for the strings, finite strings or finite sets, and another sort where you have indices into those strings. Yeah. And that turned out to be very beneficial to have a uniform approach, really to the whole of complexity classes, starting from AC0 up to X prime and stronger, etc. But what I want to do is because that's where I grew up with, that's where I've done my work. So I want to stick to this setting which Sam Bass introduced. Where you start, or where you are similar to Boolean arithmetic, you, in a sense, you have to extend the language a little bit. So the domain is still the natural numbers. You extend the language by further function symbols, and you need that in order to be able to express everything which you need to express. In particular, for example, polynomial growth rate, which a polynomial time function would always have. So what you need is somehow you want to, if you think of a number being a sequence of bits, you want to be able to compute the number of bits in such a number, and that's why you need a dedicated function. And you need something which creates your polynomial growth rate, yeah, and this is called the smash function. And without going too much detail, but if you think about, for example, you have to take x smash x and look at how many bits this has, then this has roughly length of x, so number of bits of x squared. Yeah, so there you can use x smash x in order to express quadratic runtime, for example. Yeah, and any arbitrary iterations then give you arbitrary polynomials. Yeah, so you can use those. Okay, and then we had the stratification of arbitrary formulas, which Kirby and Paris introduced, I sigma n. Here we do something similar, only we need something which is appropriate to the polynomial time hierarchy. Yeah? So instead of counting unbounded formulas, unbounded doesn't play a role anymore. It's simply too powerful. But we are counting now so-called bounded formulas. Yeah, so we are not searching with an existential quantifier an arbitrary x1, but one below a given value, a given term S1. Yeah? So if we count the alternation of such bounded quantifiers by ignoring simpler quantifiers, and here these are called sharply bounded quantifiers which have the length, which are bounded by the length of a term. Yeah, so we are ignoring those, just counting the alternations. That gives a suitable delineation of bounded formulas. So if you think about why is this simple, if this is a term, yeah, if this is a term depending on your input, let's say, yeah, it's something where you try with a polynomial time machine to compute this value, whether this is true or not, yeah. You can run a polynomial time machine to test all these values, because this is just the length of your input, that's polynomial, so you can just test on both. So all these properties are actually polynomial time, and this is what creates the complexity. And in fact, it has been known already at the time that formulas of this shape are exactly those which define the classes NP. This defines the next level in the polynomial time hierarchy of predicates, NP to the NP, etc. Yeah.
Is there a typo between the B and the P, or is that significant?
Oh, no, it's not significant. This is simply on the sets of predicates, simply on the polynomial time hierarchy. This is the formal language as a set of first order formulas. But there is, for this purpose of this talk, there is no no difference there. Okay, so we have the language, we have a delineation of the formulas. Now we can define the theories. Again, we need some set of formulas defining the non-logical symbols. It's now a bit more than pure arithmetic because we have added further symbols. For each of those symbols, we need some defining equations. And we need induction. The first is simply the standard induction as we have seen it before for pure arithmetic. This time, if we say sigma bi induction, that means that we are allowing formulas from sigma bi in our induction scheme. So that's straightforward, the adaptation of induction now to this weaker set of formulas. It turns out that we need a slightly weaker formulation of induction, and that is called sigma BL induction. And the difference is that you have the same premise of induction, but you can only conclude for all x length of x. And okay, yeah, why is this weaker? Why should this be weaker? Because if you just think about the natural numbers, you think, okay, well, we are still quantifying over all natural numbers. But there are, and I just give this as an intuition, there are non-standard models of bound arithmetic, of this type of induction, where exponentiation is not a total function. In those models, if you take the length, this is a proper initial segment. So in those models, you are not quantifying over the whole model then, yeah? And this is just as an intuition, because we are not able to actually show that this is a weaker form of induction. But morally, it should be a weaker form. Okay. No questions. Then we are in the position now to define the theories. And on the right-hand side, this is exactly as we have seen with the theories I sigma n. You just you take the normal scheme of induction and use the different classes of formulas which we defined, and these are called T12, for example, for the first, T22 for the second. And on the left-hand side with the S's, we define those theories which have the apparently weaker form of induction, the length induction. Okay, now we have all theories. What do we have? All right, okay. So before I come to relationship of the theories, let me turn to the final notion which I need to define, namely, remember when we looked at pure arithmetic, we were interested in the provable recursive functions. Turns out that that notion would be too strong here. And we need to replace it by a more restricted form of definability. So I wasn't very clear on how we define the provable recursive function, but I said it a little bit in words, but I didn't make it explicit how complicated it is actually to express it, because it doesn't matter that much in that context. Here it does matter. So we call a function sigma b1 definable in this theory as 1, 2, if we have a formula in sigma b1 which defines the graph of the function, yeah, so over the natural numbers, f of x equals y if and only if n satisfies phi xy. And in the theory, you can prove that the function is total, that every input has an output. And then you should also be able to prove that it is actually a function so that it is producing a unique value. But the crucial point is the totality. The other part is actually not, usually it doesn't give the strength, yeah, but totality is the crucial part. And then the main theorem which Sam proved when he introduced those bound arithmetic was that the sigma b1 definable function in S12 are exactly the polynomial time computable functions. Yeah, so we are in this context always speaking about functions, not so much about the decision problems. We are more interested in function classes. Yeah, and that kind of resembles the statement which I had before, that the provable recursive functions of I sigma 1 are exactly the primitive recursive functions. Here we get something similar now for the polynomial time computable functions. Yeah, and so other characterizations have also been obtained. For example, if you go up in the hierarchy, in the polynomial time hierarchy of functions, the second level are polynomial time functions which are allowed to query NP oracles in their computation, and that's this class FP to the NP. Then you can characterize, so these are exactly the functions which are sigma B2 definable in S22. So observe that the level of definability goes up in order to speak about those higher levels. And there are then also classes for P space or X time, but I won't touch on them in the course of this talk. Okay. Any questions so far? No? All clear? Wonderful. Right?
Just about the sigma P1 definable functions. If you omit last conditions, would you get something different?
That's a very good question, Anton. That's when we get to the total NP search problems. So very good. Thank you. I didn't pay it before. Very good. Yeah, very good. Yeah, no, a good question. At that time, it wasn't known because Sam was coming from the heritage as well. Yeah, people were studying functions. Only later, people discovered that kind of it becomes cleaner if you drop this and speak about search programs. We come to that in a minute. Yeah. Okay, so then to wrap up this section on boundary arithmetic. So if you take all these theories, that's easy to see that they are linearly ordered. Well, it's pretty straightforward. What's a bit harder, and Sam put a lot of work in that, is that certain levels have a good degree of conservativity, meaning they prove the same for all sigma B2 statements. Yeah, they need to do a bit of proof theory, etc. But otherwise, this forms an increasing chain. And of course, from complexity theory, we know that the separations of complexity classes like P versus NP is a big open problem. So the same question, if you translate it here, is this a strict hierarchy of theories? Meaning, are there statements in higher classes which are not provable in weaker classes? Yeah, and of course, I mentioned consistency statements at the beginning as statements which, due to Gödel, we know are unprovable in statements. Are these candidates? And of course, people tried them early on and dismissed many of the formulations. This is not completely settled, but you need to be very careful how you formulate consistency and of what theory you are actually looking at. Otherwise, it becomes a statement which is way too strong to obtain provability within boundary arithmetic. Anyway, so this is the big open problem since it was invented in 85, yeah, with the conservativity in 90. And it's similarly open as the question on complexity classes. But what do we know in terms of the relation? Yeah, you would say, okay, can we use boundary arithmetic to solve P versus NP and get the 1 million from the Clay Institute? Well, we know that if we are able to separate the polynomial time hierarchy, then we get also separation of boundary arithmetic theories. So one could say this is the boring direction. Yeah, so this wouldn't give us a 1 million. What about the other one? Well, so this was done a bit later by Bass and Zambella, and Jarek did an improvement. The collapse of boundary arithmetic theories is equivalent to a provable collapse of the polynomial time hierarchy. So if you think that through, if we are able to separate boundary arithmetic theories, then it could still be possible that, let's say, Oliver finds a very clever SAT algorithm which solves satisfiability in polynomial time. But what this then says is that it needs to use means so that its correctness cannot be proven in boundary arithmetic. So you cannot formalize that this algorithm, which collapses, which solves satisfiability in polynomial time, is solving satisfiability in boundary arithmetic. Yeah. So that's what kind of would break down. It would kind of tell us that, yeah, okay, a collapse could still be possible, but the type of algorithms which you need to find would need to use means which are beyond boundary arithmetic. And then it may become a philosophical question whether that is a reasonable assumption. But okay, I'm not commenting on that. And the final point I want to make is that there are a lot of connections to another very active research area called propositional proof complexity. You can translate boundary arithmetic proofs into sequences of propositional proofs and then ask about lower bounds, etc. It's a very active research area with a lot of progress being made there as well, which I won't touch in this talk as well. So I just wanted to mention it. Okay. Now we come to Anton, total NP search problems. But I kind of
spending it.
no, it's exactly that is actually the main focus of my talk, right? I wanted to so far it's the preliminaries. Why is this all important? What have been achieved? Now, Megiddo Papadimitriou at the beginning of the 90s introduced this type of complexity classes, search problems. They argued that there are some settings where the typical decision problems which you use in complexity theory are not suitable to reflect that. Yeah, in particular, if you have a total search problem, then it is unclear what should be the related decision problem. It's not clear immediately. Yeah? So they propose we have to study them in their own right. So how did they set it up? Okay, they say a total NP search problem. This is simply a polynomial time computable binary relation. So this is kind of the graph which we had before. Yeah. Now thinking of an input-output relation, yeah, where you have the first argument as the input and the second argument is the element which you're searching for, which needs to satisfy a couple of conditions. One is it needs to be honest in the sense of that a solution should be polynomially bounded in the input. It shouldn't be bigger. So you need to have this polynomial bound. And it should be total, meaning that for all x, there is a solution. And then the search task is given x, find a y. Yeah, and this is exactly, we will see, this is exactly dropping the condition of that this is a function, yeah, of uniqueness. So if we just briefly, I won't go into much detail here, this total NP search problem sits between P and NP in some sense, and there are some relations. For example, if all TF-NP problems would be solvable in polynomial time, then you get that NP intersect co-NP equals to P, so you get some collapse of complexity classes, and it's easy to see if you write it out. In the interest of time, I'm not doing that here. And on the other hand, if you have a collapse of complexity classes P equals NP, then you can easily see that all TF-NP problems are solvable in polynomial time as well. So it sits between P and NP with some relation in terms of separation. Yeah.
So it's not the case that if NP intersected by P's and P, but it's subset of P.
Say it again.
The reverse of the first theorem, but
well, at least I'm not able to prove it. But it doesn't hold. No, there is no. As far as I know, there's no known equivalence between those two. Okay. Now, Papadimitriou at the time, they identify several natural subclasses, and they are always defined by giving a defining principle, which is a combinatorial lemma which guarantees totality. And here are some examples. For example, the first one, PPA, is based on the combinatorial principle, and this is always on finite objects. Yeah, it's not infinite objects. So the computability theorists, you always have to think finite. Yeah, every graph every finite graph has an even number of odd degree nodes. You need to think about that, then it becomes obvious. Maybe more clear is this PLS, polynomial local search. Every directed acyclic graph has a sink, meaning a node without an outgoing edge. And so directed means the edges of the graph are directed. Acyclic, there is no cycle. So if that is the case and it's a finite graph, then you simply find a sink simply by starting somewhere and following the edges until you kind of continue, and you have to stop, and it's a kind of counting argument, because otherwise you would have to reach a cycle. You have to revisit another node, which you revisited again. So that's kind of how Papadimitriou defined them. In the context of bound arithmetic, we consider totality simply guaranteed by a mathematical theory, and that could be bound arithmetic, but could also be Peano arithmetic. So we can simply argue that totality is simply proven total in such a theory. And if we then define the provable total NP search problems, the title of my talk, to be simply the classes, so if you are given a theory T, then you simply take the set of total NP search problems which are provable total in the natural way. Then this defines a subset of the TFNP problems, and it's then easy to see simply because the theories are ordered linearly, and that implies that also the total NP search problem classes are ordered linearly. So this set is included in this set, etc. And of course, you don't have to stop in bound arithmetic. You can continue with fragments of Peano arithmetic. You can also ask what are the total NP search problems of I sigma 1 or Peano arithmetic or of ZFC, etc. It's a sensible, so a well-defined object in this way. And then, of course, the natural question here to ask is this hierarchy strict anywhere? So, for example, is this class different from the first? That's something to ask. But based on what I just said, if you're able to show this, then you would have solved that P is different from NP. So it's probably not an easy question, but maybe a good argument to say that it may be worth studying properties of those classes. Okay, so now I've introduced polynomial local search problems. And what I want to do now is, and in particular the provable version, look at a couple of characterizations of these classes done in bound arithmetic and then also in Peano arithmetic. So let's start with the total NP search problems of bound arithmetic. Now we concentrate initially on these pi bk polynomial local search problems. So that's an extension of the PLS problem that every DAG has a sink, every acyclic DAG has a sink, and this is kind of a natural extension of those. So let me explain a little bit how these problems are defined. So you have a search space, which is this F, of your potential solutions which you're looking for. And this is kind of now a combinatorial setup which should guarantee that there is always a solution, which kind of defines your search problem. Your input is the X, and you have then a combinatorial setup, and some things within this setup which provide solutions and which are guaranteed to exist. So we have the X, and we have the set of feasible solutions or candidate solutions. We have an initial value function which finds some point in this set of solutions. We have a neighborhood function, which takes a solution to another solution. Some may loop. And you have a cost function, which provides a cost for each solution. And the search task is to find a solution on which the neighborhood function is looping. And the guarantee is given, right, okay, I didn't say it here. The guarantee is given because the cost of the neighborhood function is decreasing. So the neighborhood function takes a candidate solution to another candidate solution where either the neighborhood function is looping, yeah, then you have found a solution, or it's decreasing the cost. So therefore, this defines if you take the neighborhood function at the edges, it defines an acyclic graph modulo those self loops, and the cost function kind of so it defines a directed graph, and the cost function gives you acyclicity. Okay, is this example clear? Right, and then okay, the crucial point, why is this so? Without the search space having a higher complexity, if this would be polynomial time, we simply have the setup of polynomial local search. For pi bk polynomial local search, we increase the complexity of the search space. And it may feel odd at this point, but we may see a little bit later why this is actually beneficial. Okay, so I won't go over this side. This simply makes formal all the points which I just said, in particular also the properties which all these symbols should have. I won't go into details here. So let me just go to the results. So if you take the version where the set of feasible solutions is polynomial time, so pi b0, if you want to call it PLS, then this was called PLS initially in 95 already, and Bas and Krajicek managed to show that the provable total NP search problems of T1, 2, the second level, are exactly characterized by polynomial local search problems. Yeah. Now, if you then go to higher level, and there we see how the condition that you have pi bk space is used. So if you take this setup, pi bk PLS, then this defines a provable total NP search problem in tk plus 1, 2. And why is this the case? First, it should be clear that this is a polynomial local search problem, because this is a polynomial time relation. I argued totality, and we also have, because the search space is polynomially bounded, we have all the conditions for total NP search problem. But now, why is it provable total in tk plus 1, 2? Well, the argument is simple. You simply look at the set of all costs of potential feasible solutions. Yeah, this is now a sigma b k plus 1 set. If f is a pi bk set, you want to choose the minimum of this set, and that requires roughly sigma k plus 1 induction, because that corresponds to minimization. So you can, therefore, in this theory, find a minimum value. And if you take such a minimum value, so the corresponding source, so a candidate solution of minimal cost, then this, by the properties of the neighborhood function, has to be a looping element. Yeah. So if you go back to the picture, so in this picture, how do we find a solution? Well, we simply from this set choose any value which has here. So you take all the cost values here, you choose the minimum one, and that needs to be one which is this looping. Yeah. Okay, is this clear? Yeah. So that's why this is a pi bk. Why this is a provable total NP search problem in tk plus 1. And the theorem which then Sam and I proved was that this actually characterizes all provable total NP search problems in tk plus 1. They are exactly characterized by this type of search problems, right? And there are some other characterizations which I won't go into given the time which we have. So let me actually come, so I also skip about other type of characterization for stronger theories. Let me come to the final part. How can this be extended to total NP search problems for Peano arithmetic? Well, we have a similar setup as we had for the PyBK PLS problem. Let me just bring it all up. So the difference is that the search space is now unbounded, or not bounded. So it's not polynomially bounded. It can be arbitrarily big. And instead of a cost function, we have here a polynomial time well ordering. And the setup is that the solutions, they are kind of polynomially bounded. So you now get a guarantee simply by the well-foundedness of this well ordering. Yeah, and you can use the same argument that if you have this setup, then by choosing a candidate solution of minimal value according to this well ordering, you find a solution. Yeah, so therefore it's also a total NP search problem. Now, let me go directly to what one can show with this. One thing is that this again defines a total NP search problem. I just argued for it. If we restrict to a polynomial bounded space where the well ordering is just a less than relation, then we have again this PLS problem. And if we, so there's a technical requirement that one needs to have all the properties of such a bounded local search problem being provable in S12 in a weak theory. Otherwise, you could encode too much into the standard properties, but it's a minor technical thing. So if you assume that the search problem is formalizable, then you get an exact characterization of the total NP search problem of Peano arithmetic as these formalized alpha BLS problems for ordinals alpha less than epsilon naught. And we see here a correspondence, a similarity to the characterization of the provable recursive functions of Peano arithmetic, yeah, which had a kind of similar flavor just based on recursion instead of search problems. Okay, so let me wrap up. So this setting of TFNP is quite an active research area. Actually, there's a whole generation of new researchers who have picked that up and find all kind of relations between, for example, simulation between propositional proof systems and characterizations of TFNP classes. And for example, Goes et al. Use this in order to give separations between TFNP classes relative to an oracle, not absolute, that would solve P versus NP, but relative to an oracle. And they do this uniformly for a very wide field. It's also promoted as an organizing principle between propositional proof systems and models of Boolean circuit, so proposition proof complexity and usual proof complexity or circuit complexity. And there's other work by Hubernek, Karnicki, and Tapen who prove connections between intersection classes of TFNP and proof properties like feasibility junction properties. So this kind of shows it's an active ongoing field of research where the next generation of researchers are producing results. Just in the context of what I've shown here, there are some questions which I want to work on, but it's really hard. So one thing is that if you have a good characterization of TFNP of a certain theory, you can turn this into a propositional tautology and try to prove lower bounds for a related propositional proof system. That's one of the driving factors of trying to get characterizations. And you can then use this also to get a separation between T22 and T32, so levels of bound arithmetic relativized to oracles, but of a simpler nature than we currently have. So we have separation relative to oracles for bound arithmetic theories, but there the complexity increases. We are not able to do this with for all sigma B1 sentences. And then for the last part, try to compute TF and P for other theories. And my conjecture would be that all theories which admit a so-called good ordinal analysis would also be able to have a good characterization of their total NP search problems in a similar nature as I have shown here. And with that, I stop. Thank you very much.
So thank you, Arnold, for this overview and also for the future research directions. These are, of course, the most interesting one for everyone. There was the question online already whether you would share the
yes,
slides.
Happy to share the slides. Yes.
That would be very nice because you skipped over a few, and that's what people would have found interesting. So that's perfect. So are there any questions in the audience?
Your conjecture at the end is terrific. You believe it?
Which one?
The one about
this one
being able to characterize as long as you've got a good ordinal analysis.
Do I believe it? Yes, of course.
Of course, it matters what the theories are.
Yeah.
Because when one is outside this subject, some theories look as if they are, if you like, created to solve the characterization problem for the computability aspect.
Yeah.
And others just stand there, magisterially important, like P. Arnold.
Yeah.
And I wonder, do you have any favorite theories amongst all these theories that you think have a certain kind of classic robustness
right.
As a theory?
Okay. So I think if I understand your question correctly, John, you are asking whether I have a favorite theory which is robust enough to kind of allow this conjecture to actually to work. Is that?
Well, your conjecture is general, but what I was thinking was that piano is such a magisterially important theory.
Yeah.
And the imposition of restrictions on the induction principle, which, by the way, starts with John Shepherdson, not with Kevin Bias, as so many things in logic do, by the way. These theories are self-evidently interesting straight off the bat because of piano and so on, and the results that come out. I just wondered whether some of the other theories that have been created, starting with Sam's work and so on, whether they have a kind of robust, well, not robust necessarily, but whether they can stand on their own 2 feet as interesting theories outside their role in bounded arithmetic. That's what I think I was trying to say.
Right. Okay. That's so of course a theory like ZFC would also be a theory which is, I guess, standing on its own field. But whether it's amenable to this type of questions, it's a completely different question. For example, we don't have an ordinal analysis for those theories. So I think my take on which of those, so it's probably less focused on the theory itself in the context of this conjecture, but on the ordinal analysis which you get out of them. Because in previous work, we have given characterization of the ordinal notation system in a polynomial time fashion. Yeah, so you need kind of to be sure that the concept which you use in your ordinal analysis are kind of simple enough to be formalizable in bounded arithmetic. Whether that is true for any type of ordinal analysis, I'm not sure. So there could be stronger ones for stronger theories, which would fall out of this regime, and therefore maybe this conjecture would not be true. But for example, gamma naught is an ordinal where we already know that you have ordinal notation systems which are feasible in the sense that you can reason about them. So any theory which has a good ordinal analysis and falls within gamma naught, I think would fall under this remit. But there would not be a specific theory which I can now would highlight, would say, okay, this is now just based on its concept, so important that it stands on its own. Yeah? But probably there are some which are heavily used in reverse mathematics, etc., where people would claim that they are of that nature.
Whole different dimensions.
It's a different dimension.
So, yeah,
Yeah, so we're characterizing these kinds of TFNP by these polynomial local search problems. Does that or does that mean that these are expressible in FP at all? Because one of your theorems earlier was if TFNP was a subset of FP, then you can characterize P in particular. I was just wondering if this was if this was like an approach to using that theorem, or
because the idea was that first we wanted to get a characterization, so you need to get a good characterization. Now then you want to relate it to something like FP, or you want to relate the sigma b the pi bk PLS problems to the pi bk plus 1 PLS problems, and maybe try to get maybe in a relativized setting a separation between, be able to show that they are different.
okay.
But these turn out to be really difficult questions, and so far nobody has succeeded in doing that. And not just for those, but I browsed over them. So there were a number of other characterizations, and people simply try to come up with other combinatorial principles which characterize as well, which may have a different combinatorial behavior, and you can handle in some way that you can use them for either lower bounds or separation, etc. But it turns out to be a difficult problem.
I mean, I guess again the question is, are these polynomial local search problems in FP?
In FP?
Yeah.
No. Well, okay.
Or about
if they were, we would have a collapse. So they are related, but we can. So for some of those, for example, PLS, we have oracles which separate PLS from FP. So FP relative, so there is an oracle such that FP relative to this oracle and PLS relative to this oracle are different.
Okay.
So this type, for some of the classes, they exist,
okay. Is there any further question?